I'll present about the nnInteractive implementation highlights with from this paper, nnInteractive redefining 3D promptable segmentation, which we'll all be aware of. So I'll give brief introduction followed by code implementations. The nnInteractive is a 3D interactive open set segmentation method combining diverse prompts such as point, bounding box, lasso, and scribbles. And these diverse prompts are incorporated as an additional channels to the image channels. So in addition to the image channels, we have previous masks, as well as the bounding box, scribbles, and points channels. And they are divided into positive and negative channels. Combining all these channels, they are fed to the UNet architecture. To simulate realistic prompts, they use interaction agents. I'll focus on the code implementations of the inference pipeline. As you're all aware of, the inference command is as follows, with the input of the NPZ format and the same output path. In the predict.py, it is first loads the NPZ, and which contains the images as well as the previous interactions consisting of bounding boxes, clicks, and previous predictions. And the main function is the run inference function. The run inference function inputs images and the prompts and outputs the multi-class segmentation mask. First, it initializes. I'll give an overview of the steps in run inference. First, it initializes and load model weights. Second, it sets images and buffers for predictions to initialize it. And then it runs inference for each of the objects by adding previous segmentation and adding bounding boxes and adding clicks to interactive channels. And then combining these interactive channels as well as the image, it runs prediction, and then it aggregates the results across all the objects. First, it initializes the model weights. It initiates the inference session, which is an interactive inference session, and loads model weights. And here, the nnInteractive inference session is a class that coordinates the inference as well as addition of the prompts. It initializes model using initialize from train model folder function, which builds network architecture and loads the model weights. The architecture they use is residual encoder UNet with 8 input channels, the first one for image volume and the rest for the interactive channels. And the number of output channels is 2 channels for binary segmentation. Next, it sets the image and buffer. Using setImage function, it preprocesses images and saves it to the preprocessed image variable, and then it initializes interaction channels. The setImage takes an image of dimension 4. The first dimension is channel, followed by depth, height, and width. The first is the image preprocessing, where the image is cropped to non-zero voxels, and then the z-score normalization is performed. Next, it initializes interaction channels to all zeros, where the number of channels is 7. As I mentioned before, there are 7 channels. The first channel is for previous segmentation, followed by boxes, points, and scribble prompts. They also initialize buffers, which stores the prediction. The target buffer stores the segmentation of a single object, and the results are used to aggregate segmentations across all of the objects. Next, we run inference for each of the object. We first add previous segmentation using add initial seg interaction function, and then we add bounding boxes by using add box vbox interaction function, and then we add clicks using add point interaction, and then the prediction is done using underscore predict function, and the results variable are used to store the segmentation that are stored in the target buffer for each of the object. I'll go over adding the prompts. The first one is the previous prediction. If it is the first interaction, we don't have any previous prediction, so it only runs reset interactions, which resets interaction channels and target buffers to all 0 because we are iterating over objects and each time we need to set it to zeros. And from the second iteration, we additionally add the first interaction channel to the previous segmentation results. If you see at the bottom of the slide, the interaction channels is initialized with the previous segmentation, which is initial underscore seg. Next is adding bounding boxes. The format of the bounding boxes is zmin zmax, ymin ymax, and xmin xmax. It is fed into add bounding box bbox interaction function, and this function transforms boxes to non-zero region of the crop to match the preprocessed image, and then it place 1 to the bounding box regions. Next is adding prompts. Next is adding click prompts. So the clicks and the orders are, the formats are as follows. And using this, for each of the click, we have foreground or background order. And for each of the click, we add positive click if it is foreground, and negative click if it is background, using add point interaction function. This function first transforms the point coordinates to the non-zero crop regions, and then place point function is used to place the point to the interaction channel corresponding to the click. And place point uses the distance transform with default radius 4 to place the points. Next is the prediction with the zoom out mechanism. I'll first go over the whole process. As the original patch size is 192, to broaden the view of the objects, we scale the box patch size with a zoom out factor of 1.5. So the resulting scaled patch size, which is enlarged version of the original patch size, is 288. Using this scaled patch, we crop and pad to the object. We crop and pad the image, and then zoom out process is incorporated using interpolation. This ensures that the image is rescaled to the original patch size, which will be used to feed into the network. This is the predict function where we run the inference using the zoom out mechanism. And we iterate across zoom out factors. I will not go into the details of how zoom out factor was first initiated, but it is dynamically decided based on the prompts from the last interaction. As I previously mentioned, the scale patch size scales the patch size to the scaled version, enlarged version, and the scaled patch size will be higher than the original patch size. Next, scaled bounding box is used to crop the images as well as the interaction, where scaled bbox is centered around the prediction center, and prediction center is also dynamically decided by the previous prompts. Using the scaled bbox, which is of scale patch size, it crops the images as well as interaction channels. After cropping, padding is also done to match the scaled patch size. And then the zooming out by interpolation is done for both the image as well as the interaction. Next, the images and the interaction channels are concatenated and they're fed into the network. Continue zoom is set to true if previous segmentation and the current prediction has a large difference around the borders. And if they are set to true, the zoom out factor is multiplied by 1.5. And if not, it stops the iterations of the zoom out. After all the zoom out iterations are done, final refinement is optionally done. The final refinement is done because the zoom out inference is done on the coarse resolution, the lower resolution, not the fine resolution. So in the final refinement stage, we refine the segmentation along the edges of the segmentation masks. So we first zero out the positive bounding box region, which is outside the current segmentation to 0. And then we generate multiple bounding boxes, which with size equal to patch size, which is 192. Using each of these bounding boxes, we refine the prediction by first feeding in the cropped region corresponding to the boxes, which has no zoom out factor, and then replace the old prediction on this region with a new prediction on the bounding boxes. So in summary, the nnInteractive inference pipeline consists of adding prompts and then zoom out mechanism and refinement, where additional prompts includes adding prompts for previous segmentation, boxes, and clicks channels, and use zoom out mechanism to generate refined segmentation mask is done. The predict function especially is highly optimized and has much more details. If you'd like, please refer to the predict function for more details. Thank you for listening.